Catalysts can be used to increase the rate of our chemical reaction. This is done by providing a different mechanism, different elementary steps that can be followed that have a lower activation energy. This means that it speeds up the chemical reaction by allowing more molecules to make it over to the products. They are not consumed in our chemical reaction. So they're consumed, so they get used early in a mechanism step, but they're remade in a later step. And so they do not participate in the overall reaction because they're present at the beginning and the end. So if we look at our mechanism of ozone producing oxygen, if we add a catalyst of chlorine, it is used in the first reaction, first elementary step, but then reproduced in the second. So if it is on the reactant side early on and on the product side later, this is a catalyst. And it does lower the activation energy. So this particular example comes from chlorofluorocarbons depleting the ozone layer in our atmosphere. When chlorine is present, it produces oxygen instead of keeping the ozone that we need in the atmosphere to protect the Earth. So our original chemical reaction had a much higher activation energy, but because we can use those elementary steps with our catalyst, it creates different transition states with lower activation energy to form the same product. There's two different types of catalysts that we can have. We can have homogeneous catalysts that are in the same phase as the reactant particles. So it's a uniform mixture. They hold on to a reactant molecule and typically put them into a proper orientation to make the reaction happen more efficiently. They sometimes help by starting to break the bonds. If it's a heterogeneous catalyst, it means that it's present in a different phase. So if our reactants are in the gas phase, our heterogeneous catalyst might be a solid. They react with one of the reactant molecules to form a more stabilized activated complex or transition state with a lower activation energy, allowing the other molecules to come in and react more easily. If we look at our homogeneous catalyst, in this case, it is in the same phase as the reactants in the gas phase. And if we look at heterogeneous, now we have a surface, a solid surface, where the reactants can come in and then leave. These catalysts are extremely important in industry in order to make products that we use every day. One important catalyst that you use when you drive that you may not think about is a catalytic converter in the exhaust system of your car. It takes unburnt fuel and unwanted products like carbon monoxide and NOx, nitrogen containing compounds. It passes them over a ceramic substrate that has got metals, precious metals in them like rhodium and palladium and platinum to produce more environmentally benign chemicals like carbon dioxide, water, and nitrogen. Helps us to eliminate the pollutants in the exhaust system of our vehicles. Let's look at an example of a heterogeneous catalyst. They are extremely important in industry because they decrease the amount of energy required to produce new products, and they also make the reaction happen under safer conditions, like lower pressure and lower temperature conditions. So this example is the hydrogenation of ethene. So it absorbs onto the surface, it adheres to the surface of our catalyst. The molecules of hydrogen are broken apart and start migrating around the surface, and this is what we call diffusion. They come in contact with each other and are able to react. And then once that reaction has occurred, that molecule, which is now ethane, desorbs from the surface and is able to go on to be purified. Now, this is a really important reaction for fuel sources as well as making starting materials for other products in industry. Catalysts are important to you in your everyday life because they allow the biological molecules in your body, which are large and complex, in order to proceed and produce products at a reasonable rate. So the protein molecules that catalyze these reactions are called enzymes. They work by taking substrate molecules, so molecules within your body. They enter an activation site that changes the position of that substrate, orients it so that a chemical reaction can happen at body temperature and under normal pressure conditions. These would not occur if we did not have these biological catalysts known as enzymes. So we take an enzyme, we react it with the substrate, we make an intermediate of the enzyme substrate that happens fast. Then the enzyme works on that substrate and produces a product, and this is our rate determining step in the chemical reactions in your body. This is sometimes referred to as a lock and key mechanism. The substrate has to have the proper shape in order to fit into the active site of the enzyme. Once it has entered the active site, makes an intermediate of the enzyme substrate complex, which can distort or twist the molecule, which weakens the bonds and allows products to be formed. In our body, one example, there's lots of examples, but one example is the hydrolysis of sucrose. We take sucrose, which is made up of a glucose portion of the molecule and fructose. That sucrose fits into the enzyme. The enzyme allows the bond to be weakened and broken so that we end up with the two individual parts that can be used in our body. So we can use the glucose and we can use the fructose.